This is section 6.3, entitled Exponential Functions, and let's get right into it in helping you with some of these homework problems. In the first set of problems that you're going to do, if you'll read the directions, you are asked to determine whether the given function, represented by this table of values, set of ordered pairs, you're supposed to determine whether or not this function is linear, exponential, or it's possible that it's neither. So if it is linear, write a linear function, and if it's exponential, write an exponential function. All right, so here's how you can tell. I think the easiest way to go about it is first test the exponential function. And I've given you two different really tests that you can perform and see which one it is, or it could be that neither one of these apply, and so therefore it would be neither. What do I mean by ratio of outputs? Remember, output is another way of saying the y coordinate of this ordered pair, or in this case it says h of x. Ratio of the outputs means that when I do, for example, this second output divided by the one before it, I get the result of 4. When I do that same thing, just slide down by one number, and this time I'm going to do 4 divided by 1, that's 4, 16 divided by 4 is 4, 64 divided by 16 is 4. So every time I did that ratio, that little division problem, I got the same result, which was 4. All right? So exponential functions in general, using variables, look like this. A times B raised to some power called x, and the b number that we just came up with by doing this division is what b is. Okay, so I've established that we do have an exponential function. My only question is, will I have a number besides 1 that will plug in for a? I know what b is. B is just 4, and then I'm going to show 4 being raised to the x power. But sometimes there will be another number here. If it's 1, then it's just understood to be 1. It won't be showing. But how do I know if it's something other than 1? To me, the easiest way is to look at your table and look at the input for 0. Input 0 gives me output 1. And if that matches, if that holds true, when I do input 0, 4 to the 0 power is 1, then I know that my a number, the coefficient in front, this factor in front of 4, is just 1. And I don't need to show the number 1 if a is 1. Okay, so let me just do a what if. If, for example, I know it doesn't match the rest of the table, but if this number had been 2, well, now when I input 0, I'm supposed to get an output of 2. Well, as it is, I'm only getting an output of 1. So that means that a in this particular case must be 2. And I would show it like this. 4 to the 0, remember we always do powers first, and then whatever that result is, we multiply by this number. Now I would have the correct function, y equals 2 times 4 to the x. But just wanted to give you a what if. As it is, though, this is my final answer. Okay, let's do another one. Doing that same little process, ratio of the outputs, 4 divided by 2 is 2, 6 divided by 4 is not 2, so I don't need to go any further. I know this can't be exponential. So let's see if it's linear. Linear means this is delta, remember, that means the change in y divided by the change in x. That's just another way of saying y2 minus y1 over x2 minus x1. 4 minus 2 over 0 minus negative 1, and I get 2 over 1, which is 2. And to save a little bit of time, if I keep on doing that, maybe coupling up these, 6 minus 4 is 2 over 1 minus 0, 2 over 1 is still 2. And I'm going to get that same result. It's called a constant rate of change, and that's just another phrase for slope. So I know the slope is 2. It's got to be linear. And now I'm going to use one of these ordered pairs. It doesn't matter which. And to come up with the equation. So maybe just take this top one. Y equals mx. Solve for b. B is 4. So my final answer here is going to be y equals 2x plus 4. All right, so that helps you hopefully with these first few problems. Let me just run through, this is a review of graphing. In this case, I'm showing exponential growth, and the number that's immediately below x, I'm using the variable a in this case. I know before we showed exponential functions like this, so maybe just to stay consistent. A just stands for a number, but since it matches now with our previous definition of exponential functions, I'll just make it look like this. So whenever the number directly underneath x is greater than 1, you're going to have what is called exponential growth, and the graph should take on this basic shape. So I just gave you an example here. Y equals 2 to the x. Here's 3 inputs for x. Plotted those, and exponential growth will always approach positive infinity on the y pretty fast for small increments of x going to positive infinity. So as x goes to positive infinity one at a time, the graph is going on the y-axis to positive infinity pretty fast. That's why we call it exponential growth. And then coming this way, as we choose smaller numbers for x, we're just going to get closer and closer and closer to the x-axis, but we will never get there. That's called, x-axis in this case is called a horizontal asymptote. Other information, here's horizontal asymptote, the line y equals 0, that's just another way of saying the x-axis. The domain will always be all real numbers, and then just pay attention to the range. Here, we're not including 0 as part of the range because we're never going to get to 0. We're never going to touch the x-axis, and then it's just going up positive infinity on the y. Okay, when that number, and I'll just show it like this, here's some number directly underneath x. When that number is a fraction between 0 and 1, we have what's known as exponential decay. And so here is what exponential decay looks like. It's really kind of the opposite of growth. This time, as we choose more positive inputs, we're just going to keep getting closer and closer to the x-axis. That was just the opposite case with exponential growth. As we choose more negative numbers, now the graph is going up pretty fast. Okay, so here's some examples, some ordered pairs. Domain and range are the same horizontal asymptote, it's the x-axis. And now these are just the effects of growth and decay when we put a negative in front. A negative in front, remember when it's not enclosed in parentheses, it always has the effect of flipping the graph over the x-axis. And so just think exponential growth, which looks something like this, and pick it up and flip it over the x-axis, and you will have what is known as negative growth. The classic example in our real life situation is the national debt. It's growing exponentially, but it's growing in the wrong direction as far as we're concerned. It's growing in a negative direction. And then the same thing is true for negative exponential decay. It's decay, which did this, and it's flipped over the x-axis. Okay, and that's the effect of this negative in front. Notice how the range changed when we have the negative growth and decay. Domain stays the same. Okay, so we're going to graph these using translations, transformations, and you might want to pause. This is a review of translation principles that we've talked about with other parent functions. You might want to pause for just a second and make sure you remember this affects the size, but not the shape. This number h will do a horizontal shift, and be careful because it's really the opposite of the way it looks. And this number k will indicate a vertical shift. So the way I'm going to graph this function f of x equals 3 times 1/2 raised to the x power. I'm going to start with the graph of what I'm going to call the parent function, f of x equals 1/2 to the x. So just some basic order pairs. If I input 0, I get 1. If I input 1, I get 1/2. If I input -1, I get 2. 1/2 to the -1. Remember, you flip it and raise it to the first power in this case. So -1, 2, and 1, 1/2. And I'm just going to use these 3 points. You could do more if you need it. But what this tells me to do, this is called a vertical stretch when I multiply it by a number that's not a fraction. Essentially, and I've spelled it out for you here, if you just take these 3 points that we plotted and multiply just the y coordinates by 3, then you'll have the graph of this function. So here, I've got the point -1, 2, but when I multiply by 3, it makes -1, 6. Here is the point 0, 1, but when I multiply by 3, I get 0, 3. Here is 1, 1/2, but when I multiply by 3, I get 1, 3/2, which is another way of saying 1.5. So I'll just erase those red dots. They're just like reference points. And I haven't shifted horizontally or vertically. I've just changed the size. I've stretched it vertically. And so I'm still going to have a horizontal asymptote, which is still the x-axis. Okay? And so this is, to me, an easy way of graphing using transformation principles. Okay? Once again, I'm going to start with this function. Just take out what is the parent and do a little table. 0, 1, 1, 4, -1, 1/4. All right, plot those 3 points. 0, 1, 1, 4, -1, 1/4. So this is classic exponential growth. Notice the number underneath, x is greater than 1. Okay, so the -1 in the exponent indicates a horizontal shift. So all of these points are going to be shifted 1 to the right. Be careful about horizontal. So I'm going to go 1 to the right, and I'm going to go 2 up. This number k, not part of the exponent, will indicate a vertical shift. So each one of these blue dots are going 1 right and 2 up. 1 right and 2 up. 1 right and 2 up. And I can erase those blue dots now if they're causing some confusion. Now, you got to be careful because the entire graph shifted up 2 places. So what used to be a horizontal asymptote right here is now shifted. We now have a horizontal asymptote right here. And so my graph is going to always approach y equals 2. And I really shouldn't have touched it, but you get the idea. I should not go below y equals 2 on the graph because my whole graph shifted up 2 in addition to shifting right 1. So that's an example of graphing using translations. Okay, so to finish up this lesson, I need for you to show how to solve for x by using what is known as, by some, the common base method. In this equation, I have 2 numbers that are bases. 3, a base is just a number that's directly below an exponent. So I have 3, and then you may not realize it, but 81 is a base because it has an invisible exponent of 1. Well, I'm going to rewrite this equation so that the same base appears on both sides. So I'm going to change 81 into a base of 3 being raised to the 4th power. That still equals 81, but it's using a base of 3 as a different way of writing 81. When you get to common bases, like we have here, to solve for x, just think about putting the exponents equal to each other and solve. And I need for you to show this work This will be good practice for you. And so my final answer is, for x, is -4. Okay, same idea here. Rewriting this so that it's the same base on each side. I'm going to do 5 to the x plus 3 equals 5 to the -1. I just found a different way of representing 1/5 using 5 as a base. Now that the bases are the same, I take the exponents and I make them equal to each other, and I solve for x, and once again, I got x is -4 as my solution. All right, let's try this one. This time I'm going to rewrite both of these so that it's a base of 2. 4 is 2 squared x to the second, and this already has a base of 2. Okay, so now that my common bases have been identified, I'm going to take these exponents now. Let me just highlight what our equation is going to look like. I'll circle it. I'm going to be solving 2x squared equals x. Okay, well, to solve for x, I need to make my variables show up on the same side of the equation. So I'm going to subtract x from both sides. All right, I'm going to do a little factoring because I have a GCF. Okay, and I'm going to solve each of the factors. Just pretend like each factor. I've got 2 factors here, x and 2x minus 1. I'm going to let each one of them equal 0. That's pretty easy. One of my solutions for x will be 0, and now I'll just let the other factor equal 0 and solve. So I got 2 answers in this case. X is 0, that should make this true. 4 to the 0 is 1, equals 2 to the 0. Okay, that matches. And then if I did input, I can check this and make sure it's right. If I let x be 1/2, do I get the same thing? Well, 1/2 raised to the second power is 1, so this makes 4 to the first. Sorry, I need to back up. 1/2 to the second is 1/4. Okay, so it's like 4 to the 1/4 is equal to 2 to the 1/2. All right, and so you might want to just, if you're checking this, you can grab your calculator and see if the 4th root of 4, which is another way of saying this, is the same thing as the square root of 2. And you'll check that out with your calculator and you'll see that that does check. So my 2 answers here are x is 0 and x is 1/2. Okay, got one more. Let's change these into base 3. And the way I do 27 is 3 to the 3rd. Now remember, there's already an exponent 2x there. Okay, so now that I've got common bases, I'm just going to let the exponents equal each other. And 3 raised to the 2x makes 6x. Okay, I'm going to have a quadratic equation. So I'm going to set it up in standard form and solve by factoring. The factors of -7 that add up to -6 are -7 and +1. So I got x is +7 and x is -1 as my 2 solutions. Okay, so it's all about changing to common bases. I hope this helped you out. And if not, you're always free to email me, and come tomorrow and we'll check it out.